All right, let's talk quickly about some basic identities under trigonometry. We have several identities in trigonometry, and in this video, we'll be talking about the basic ones, about 7 of them. And one of the things we'll be doing is to derive some of these basic identities. Now, let's look at this right angle triangle with sides A, B, C. So from here, I'm sure we can recognize that the C here represents the hypotenuse, and the A represents the adjacent, and the B represents the opposite, which is the side opposite the angle. And we have of course, we are dealing with the angle theta right here. Now, let's try and walk through our trigonometry ratio, which I believe we all know, the SOHCAHTOA. Now, the SOHCAHTOA, obviously, it's a short for representing how the trigonometric functions are meant to move. So we have this S representing the sine of an angle, the C representing the cosine of an angle, the T representing the tangent of an angle. And obviously, from what we have right here, what we can derive from here is that the sine of any angle will be equals to, the whole here stands for the opposite over the hypotenuse. And then the cosine of any angle will be the adjacent over the hypotenuse. And then the tangent of an angle will be the opposite over the adjacent. So this is the basic trigonometry ratio we all probably know about. And let's quickly apply that to this, our right angle triangle. So from what we have here, if we decide to solve for the sine of this particular angle theta in this right angle triangle, our sine theta will be equals to, this is the opposite, that will be B over the hypotenuse, that is C. Then our cosine of theta will be equals to A over C. And then the tangent of angle theta will be equals to B over A. Now, let's then go on to try and derive our very first identity. So let's decide to move on from, let's just do sine of an angle divided by cos of an angle based on this right angle triangle. So the sine of this angle theta divided by the cosine of angle theta. Obviously, from what we have here, the sine of angle theta will be B over A divided by A over C. You can bring that to simplify it further in this format. And I think the sine of an angle is not B over A, it's actually B over C. B over C. Sorry for that. So we have B over C multiplied by C over A. Then the C can cancel C, and then we'll be left with, the C can cancel C, and then we'll be left with B over A. So we can say sine of an angle theta over the cos of an angle theta is equals to B over A. Now, when you look through on this, you can see that the B over A right here is the same thing as the B over A that was represented with tan theta. So we can therefore conclude that the tangent of an angle is equals to the sine of an angle over the cos of an angle, seeing that the tan of an angle theta was B over A and sine theta over cos theta was also B over A. This gives us our very first identity. So this is identity 1. That is our first identity. So let's go on to prove the other identities. So before I go on to prove some other identities, let me state some basic identities that we will not be proving. It's just something you should know. And that's the reciprocal of these 3 angles. So the reciprocal, some people will call them the inverse. They will say sine. I think it's actually reciprocal, not inverse. But anyhow you want to call it, when you have the reciprocal of sine, when you have the reciprocal of cosine, when you have the reciprocal of tangent. So what are the results of this? Well, when you have the reciprocal of sine, you'll be having what we call cosec of theta. Cosec theta. And then when you have the reciprocal of cosine, here we would have the secant of theta. So this is cosecant and this is secant in full. And then when you have the reciprocal of the tangent, we have the cotangent, which we call cot theta. So this gives us three more identities. So we have this as one identity, also this as another one, and this as the fourth one. So we have four basic identities already. So let's go on to prove the remaining three of them very quickly. So using Pythagoras theorem, and Pythagoras theorem basically stated that when you have the hypotenuse square, you will be having the opposite square plus the adjacent square. So looking at this, you can see that the hypotenuse in this particular question was the c. So that means we have c square will be equals to b square, that was the opposite, plus a square. So this is by following the Pythagoras theorem. So we're going to do something very quickly. We're going to divide this entire theorem. We're going to divide this entire thing by c. We're going to decide to divide through by c square. So we're going to be dividing what we have here. That's c square over c square will be equals to b square over c square plus a square over c square. So that's just the next step. When you decide to do this, you'll be getting this cancelling each other, obviously, and then we'll be left with b square. That will be 1 equals to b over c all square plus a over c all square. Now, looking at what we have derived here from our SOHCAHTOA, you can see that b over c, which we have here, represents the sine theta. So obviously we can rewrite this as 1 equals to sine theta all square plus a over c represents cos theta. So we have cos theta all square. Now I want you to understand that when dealing with trigonometries, sine theta all square can also be written as sine square theta. And the same goes for the other trigonometry functions. So cos theta all square will be cos square theta. So we can rewrite what we have here as 1 equals to sine square theta plus cos square theta. And this is our fifth trigonometry basic identity. Don't forget, we have already talked about 4 of them. So this is the fifth one. That's sine square theta plus cos square theta equals to 1. What if we decided not to divide this particular equation with c square? What if we decided to divide it with b square instead? Let's see what that will bring out. That will be c square equals to c square over b square will be equals to b square over b square plus a square over b square. Now we're dividing through by b square. Now this will give you c over b all square equals to 1 plus a over b all square. Now if you look through on what we have here, you can see that we are having c over b, b over c, c over b right here, b over c. Now if you can decide to do 1 over, let me write that here. If we have 1 over C over B, that means the reciprocal of C over B, what are we going to get? This will be B over C. So obviously, with what I just said here, 1 divided by what you have here, or probably we move in a different route so that you would understand better. If we decided, don't forget, this is what we're trying to get. So if we decided to do 1 over B over C, 1 over B over C will obviously give you 1 divided by B over C, and that will be 1 times C over, that will be 1 times C over B, which is what we have here. Definitely, I'm sure you can see that C over B here was sine theta. That means if we say 1 over sine theta, we are also going to be saying C over B. Don't forget, when I decided to say 1 over B over C, which was sine theta, I got 1 divided by B over C, and I was able to arrive at 1 times C over B, which was what we have here. So therefore, I can rewrite this as, instead of writing my C over B now, I would not be wrong if I decided to write it as 1 over sine theta. Don't forget, sine theta is B over C. So 1 over B over C will obviously give you C over B. The same thing goes for A over B. I want you to know that A over B is, if we do the reciprocal of tan theta, which was B over A, if we do 1 divided by B over A, you can do that. Let's try and do that here. If we do 1 divided by B over A, we'll be getting 1 times A over B. And that will be what we have here. So 1 divided by B over A, which was tan theta, we can easily write A over B. Instead of writing it as A over B, we can write it as 1 over tan theta. So looking at what we have here, we have been able to dissolve this particular equation. This is C over B. It's now 1 over sine theta, because sine theta was B over C. Obviously, the reciprocal of B over C will be C over B. This is A over B. Tan theta was B over A. The reciprocal of B over A will obviously be A over B. So I can rewrite A over B as 1 over, maybe in case you wanted to have, in case I should have written 1 divided by B over C before I wrote this, and 1 divided by B over A before I wrote this. But I'm sure you can understand that tan theta is B over A and sine theta is B over C. Now, don't forget, I already gave you a function, one of our identities, that was the same thing as 1 over sine theta, and that was cosecant. So that means I can write this as cosecant theta all square will be equal to 1 plus the reciprocal of tan theta. We wrote it as cot theta, that's cotangent theta. So you can see now that we won't be wrong if we decide to make a conclusion that cosec square, don't forget, cosec theta all square is the same thing as cosec square theta. So I can write cosec square theta being equals to 1 plus cot square theta. And this is another of our basic identities we have been able to prove out. So this is the 6th basic identity we'll be dealing with in this particular video. Now, what if we decide to divide through by a square rather than dividing by, we have divided with c square, we divided with b square, let's decide to divide through with a square. So we're having c square over a square will be equal to b square over a square plus a square over a square. Here we'll be having c over a all square will be equals to b over a all square plus 1. Now, This obviously can be written as 1 over A over C, and this can be written as 1 over A over B plus 1. Now looking at what we have here, A over C is the same thing as cos theta. So I won't be wrong if I decided to write cos theta here. And A over B, well, we don't have A over B here, so I think what we had to do would have been, we could have left it at B over A because we have B over A represented here. So we don't have to make the reciprocal of B over A. So we can leave it at B over A square, which will be represented with tan theta. So we can have tan theta all square instead here. Now, from what you can see right here, you can see that obviously 1 over cos theta, the cosine of angle theta, is the same thing as sec theta. Everything all square will be equal to tan theta, everything all square plus 1. So I won't be wrong if I deduce my last identity by saying sec square theta equals to tan square theta plus 1. So these are the 7 basic identities we will be dealing with under trigonometry. So in summary, we can define all our identities very quickly. Our tan theta equals to sin theta over cos theta. Cosec theta will be 1 over sin theta. Cot theta will be 1 over tan theta. Sec theta will be 1 over cos theta. And then we have sin square theta plus cos square theta equals to 1. That's number 5. Then we have 1 plus cot square theta will be equals to what? Cosec square theta. And then we have finally 1 plus tan square theta equals to what? Sec square theta. So these are our 7 basic identities which we'll be making use of in several applications on trigonometry. Thank you guys for watching. I hope to see you in the next video. Bye-bye.